Okay, so let's simplify radicals now where we have variables and potentially some numbers. So we're going to have some just variables and then numbers and then with variables, and what do we do? So we can actually kind of go back to the logic of factoring perfect squares. So what do I mean by that? So let's kind of go back to something like the square root of 25. This is going to kind of help us understand how to do with variables. So we know that the square root of 25 is also the same thing as saying the square root of 5 times 5. And we remember that when we're talking about the square root, we're just looking at just one of these values, which would be like the root of the square or just one side of the square. Now, the thing about that is as you get into higher roots, that can get more complicated, but the procedure will be very similar. So we will kind of look at it recognizing that the square root of 2 5s is just 1 5. So we can kind of think of this in the same way, right? I can say x times x times x times x. So I have these 4 x's that I'm being multiplied, repeated multiplication, and if I just break it up to 2, right, I have, how many x's do I get from the square root of this? I get 1. And how many x's do I get from the square root of that? I get 1. So I get x squared. So the square root of x to the 4th is x squared. And it's actually kind of useful for us to think about a pattern. So let's just take the square root of x to the 4th and look at the square root of x to the 6th. If we wrote it out, right, we have 4 x's, so we'd have 6 x's here. So I'd have x times x times x times x times x times x. I am not going to do this every single time, but I'm going to help you understand the concept so that you can yourself actually make sense of this. But again, for every 2 underneath the radical, it's 1 outside. Every 2, it's 1 outside. Every 2, it's 1 outside. So I'm left with x to the 3rd. And actually something interesting here is, what do I notice is that on the first one, x to the 4th, this is half of it. X to the 6th, this is half of it. So we can kind of extrapolate, which means to kind of predict outside our pattern, and I'm going to get x to the 4th. X to the 10th will be x to the 5th. Notice these are just cut in half. I did use only even exponents because what happens if I have a number like x to the 5th? So let's kind of look at that, but once we get way over here. So let's kind of look through these examples and then we'll kind of look at that idea. What happens if I have a number like the square root of x to the 5th? But let's go back and break this into 2 parts. Let's break it into what we understand. We can multiply these 2 to get this, so we can factor it in the same way. And then we can factor this going back to the perfect squares. And if you're not sure of perfect squares that go into 40, the highest one is 4 times 10. So I get 2 square roots of 10. And then q to the 6th, well, if we just use the logic, what we talked about, of x to the 6th, that's just going to be q to the 3rd. So I have this times q to the 3rd, but we're going to reorganize it because this and this are not under the square root symbol or the radical symbol. Later on, it won't necessarily be a square root if I change the root, but it's more of a radical symbol than a square root symbol. But if I put everything that's outside, we put it in front, and then everything inside, that's the simplified form. It's not like super difficult, but it does require just having some ideas. So let's factor this one, the square root of 60 times the square root of h to the 12th, right? Just break up the numbers and the variables. And then the square root of 60 can be broken into factors where I find a perfect square factor, and of course go to half of that, so 30, then 25. So the first one I actually can find that goes into the square root of 60 is the square root of 4 again, right? So sometimes it's small perfect squares. It's just easier than prime factorization in many ways, and so I'm left with this 2 square roots of 15. And of course we can factor this to h to the 6th because it's just going to be cut in half. So we have these values, right? So these need to be put together, and this is outside the radical, and so is this 2. So let's put all the stuff outside the radical in front of the radical, and there is our answer. 2 times h to the 6th power times the square root of 15. And where over here we had 2 times q to the 3rd power times the square root of 10. And now we do have this odd exponent. And so let's kind of break it up and we'll get the odd value exponent so that we can kind of see how it works, and then we'll kind of extrapolate that pattern. But we can break this to the square root of 9 times the square root of 2, where 9 is my perfect square. Notice I am pulling out perfect squares first when I'm factoring it because it's useful. Because I know 2 of these, I want one of those as the perfect square root, right? And so I have 3 times the square root of 2. But what about this? So I can factor this to y times y times y, right? Underneath there. And if I break that up, I have y times y, right? Remember 2. And then I'll separate it. So what ends up happening is when I have an odd one, I can pull out 1 and I'm left with 2. And we know that this is y and this is what's left over. So this 2y's become 1 outside the radical, right? Just following our same logic that we talked about, where if I have the square root of 2 5s, I get 1 5 because the square root of 25 is the same process. This logic carries forward, and so I have all these values. So what do I do for organization? Well, this y and this 3 are outside, so I'm going to put those outside the radical symbol, and then underneath the symbol where I would have the second root of 2 and then y. And I always put the numbers in front of the variables. It's good organization, and later on we'll kind of go through organizations purposes for that. But if we kind of look at, I'm just going to create a little pattern here for you. So if I take the square root of x squared is just x. The square root of x to the 3rd, well, that's going to be x times the square root of x. Because one way to think about this is I have x squared, right? I have the square root of x squared. Let me make this look a little bit better so it doesn't look like they're inside each other. So I have the square root of x squared times the square root of x, and of course we know the square root of x squared is x. So if I then go to the square root of x to the 4th, well, that's just x squared. If I go to x to the 6th, the square root of that, that's x to the 3rd. So these are all cutting it in half, but what happens if I want x, the square root of x to the 5th? Well, that's going to be really similar. It's going to be, I'm going to set it up so you see, it's going to be x to the 4th times the square root of x. And we already know the square root of x to the 4th is cut in half, so it's x squared of x times x. So let's try x to the 7th and the square root of that. Well, I can break it up to x to the 6th times x to the 1st. And I'm just going to put that square root symbol here. I guess I could have done that over there, but I'm just showing you here that this procedure and this procedure really are similar. They're just one step away from each other. But I'm going to break it up to this times this, and then x to the 6th is x to the 3rd, so this is just x to the 3rd times x. And you can see if you have an odd number of exponents, you're going to be left over with this 1 square root of x and the one number minus, right? So I could say, let's try x to the 9th, the square root of that. If I take away 1, I have x to the 8th, right? And that times x, which is just x to the 4th times the square root of x. And hopefully you see this pattern where I can take away 1 from this, which gives me 1 inside the radical. And then what I'm left with, I can cut in half to get my value. And so those are kind of our simplifying procedures for simplifying radicals with variables and with numbers at the same time. So that should help.